let's try to solve this given homogeneous differential equations, and then we're going to consider here that it's already given that the roots that will be specified later on are repeated, and then they are both, or they are all real. But of course, we're going to verify that for this situation if this is true. The purpose of just presenting this idea is because we have a lot of differences if we talk about our roots to be real and repeated pertaining on the equivalent auxiliary equation, because there are 4 different instances. The first one, if the roots are real but they are all distinct. The second one is this. The third one is when the roots are imaginary. And the fourth one is when the roots are imaginary and some of the imaginary roots are also repeated. So there are different types of general solutions, and we're going to use here the solution for repeated real roots as soon as we have verified that to be true. The first step here is to come up with an equation using a differential operator D. But let's try to also be reminded here that our dependent variable in this case is x, and our independent variable is t. So our equation with differential operator D would be f dx equal to 0, as this is our dependent variable, not y. And later on in our solution, we'll be using t instead of x and x instead of y. We'll have it later. Okay. In short, our given equation here, since this is a 4th degree, so you will have here d to the power of 4 plus 2, this is cube, so d cubed plus d squared is equal to 0. Okay, sorry, I forgot again to write here the dependent variable x equal to 0. This is very important because, again, that's your guide later. Then after this, let's write the correct auxiliary equation where we use f of m. Therefore, our auxiliary equation now would be m to the power of 4 plus 2m cubed plus m squared is equal to 0. We'll be solving for the roots of this given equation now, auxiliary equation, and to see later on if there are really repeated and real roots. So there are a lot of process involved in factoring this or in solving for the roots of this. The first one is, of course, the common monomial factoring. Let me write it here. You will have m to the power of 4 plus 2 m cubed plus m squared is equal to 0. If we're going to factor m squared, you will have here m squared plus 2m plus 1 is equal to 0. Okay? It's easier to do that because, again, the first type of factor we always need to consider when we factor is the common monomial factoring. And at the same time, later on, there is a good interpretation with that. Let's continue. Since it is a trinomial, or specifically a perfect square trinomial, we can factor that into this manner. You have m squared times m plus 1 times m plus 1 equal to 0. Of course, that's a perfect square trinomial, or if you don't want that process, of course, by AC way, your a there is 1 times 1, you will have 1. Factors of 1 when added will result to 2, so basically it's just 1 plus 1. That's why you have here m plus 1 and then m plus 1 here. Okay, now from here, we can also break this into 2 m's. You will have m times m plus 1 times m plus 1 equal to 0. With this, we can now solve for the roots. The first root is when it is 0. Okay, this one here. The second is, of course, when it is 0 as well. The third one, when m plus 1 is 0, so your third root is negative 1. You also have here the fourth one, m plus 1 equal to 0, so your fourth root is negative 1 as well. As you can see, there are 2 roots that are repeated. Hence, it follows the claim that they have repeated real roots. So with this, we are going to use the specific process or specific general solution for situations like this involving repeated real roots. And it's in general form just like this. Take note that our dependent variable is x. Our solution should be x is equal to, okay, here is the situation now. X is equal to, you will have e to the power of mx, okay, times, you will have c sub 1 plus c sub 2 x plus dot 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 plus c sub n x to the power of n minus 1. This is for, this is where, again, very important to be guided because our independent variable is t, so this would be mt c sub 2 t until t here to the power of n minus 1. Okay. However, there are two roots that have been repeated, so we'll have two situations like this. And since we only have the multiplicity of 0 is just 2, so we'll end up until here. The multiplicity of negative 1 is also 2, so similar thing here. So here's the solution. Okay, so x is equal to, let's start with 0, e to the power of 0t times t. Then you will have c sub 1 plus c sub 2t. Okay. Then the second part would be for this, following the same pattern, e to the power of negative 1t. Then you have c sub 1, no longer c sub 1. Let's have c sub 3 because c sub 1 is already used, and c sub 4t. Hence, your solution now is this just 1. So you will have c sub 1 plus c sub 2t. In this case, you will have plus e to the power of negative t. Then you have c sub 3 plus c sub 4t. Of course, you can always distribute that, but this is already okay. But if you really like to distribute that, you have c sub 1 plus c sub 2t plus e to the power of negative t, c sub, let's start with the constant c sub 3. C sub 3 e to the power of negative t plus c sub 4t e to the power of negative t. But of course, again, it's already okay to end up here. And here's the solution of our given homogeneous equation. Please be guided of the notation. X here is our dependent variable and t is the independent, same as what is already declared here in the given. Thank you very much for watching.